Linear classification. When we were learning about linear regression, what did we try to do? We tried to come up with the best fitting hyperplane, that is in two-dimensional space, the best fitting line. So whenever we had a training data, we tried to come up with a hyperplane which would fit the best with the given data. That is, if this is your given data, this is your two-dimensional space and this is your data, then what did you try to do? You tried to come up with a line, something like this, which would best fit all these lines. This is what you tried in case of linear regression. Coming to linear classification, what you will do, we'll try to come up with the decision boundary that divides the input space into decision regions. That is, you have to draw a line. The task is the same. The only difference is, instead of finding the line which best fits the complete data, this time this line should be the decision boundary which will divide the whole input space into two regions. And what is the speciality of these regions? First region should belong to class C1 and the second region should belong to class C2. Let us draw a graph in that case. That is, if this is your two-dimensional space, now we are talking about classification, linear classification. Let us say red colored points belong to class C1. So all these points, all these red points, they all belong to class C1, let us say. And let us say I have a lot of blue points. All these blue points, they all belong to class C2. And what is my task? I want to draw a linear decision boundary, that is in two-dimensional space, the decision boundary would be a line. And this line should divide this data into class C1 and C2. So if this is my decision boundary, the line would go something like this. It would be like this. What is the speciality of this decision boundary? If you go into this region, the region above the line, that belongs to region R1, which is class C1. And the region below this line, this is region R2, which belongs to class C2. So if you compare between linear regression and linear classification, the task that you're doing is same. You're trying to draw a line. Line in the sense, if it is a higher dimensional space, a hyperplane. In two-dimensional space, your decision boundary is a line. In case of linear regression, you will draw a line which will best fit your data. That is, if this is the graph, then if this is your total data points, you will try to draw a line that will best fit your data. This is linear regression. In case of classification, what will you do? You will try to draw a line which will divide the input space into two regions. And what did that do? It divided into one region which has class C1 and the other region which has class C2. If I give you a new point, let us say I put a point here and I asked you whether it belongs to class C1 or C2, what will you do? You will see whether it belongs to the region above or the region below. Because this point belongs to the region below my decision boundary, what will I say? It belongs to class C2. This is how you do linear classification. So coming to the decision surface, the decision surface in case of a d-dimensional input space would be d-1 dimensional hyperplane. This is the way you do in linear classification. What is a d-1 dimensional hyperplane? If your input space is a line, then what is d-1 dimensional hyperplane in that case? A dot. If your input space is two-dimensional, that is in this picture, your input space is two-dimensional. In that case, your hyperplane, the d-1 dimensional plane, that is input space is two-dimensional, then your hyperplane would be one-dimensional. What is a one-dimensional hyperplane? It is a line. That is what you try to draw here. Your line divided in the input space into two regions. Similarly, if your input space is, let's say, three-dimensional, then your hyperplane which separates it into two regions should be two-dimensional. What is a two-dimensional hyperplane? It is a plane, right? So this is the logic. Next question is, this is a very important question, that is, on what sort of data can you apply this technique of linear classification? Whenever you are learning any technique in machine learning, it's important to understand where to apply this technique. See, if you simply know a technique, what is the point if you don't know when to use it? That is the whole point. You should know when to use which technique and you should choose wisely. Where should you use linear classification? You can use it in case your data is linearly separable. What is a linearly separable data? That means any data set whose classes can be separate exactly by a linear decision surface, that is said to be linearly separable. For example, the data that you have in this graph, this is linearly separable data. Why is it linearly separable? Because there is a linear decision boundary, a d-1 dimensional hyperplane, which can exactly divide the data space into class C1 and C2. See, on one side you have only class C1 and the other side you have only class C2, which means this linear decision boundary can very clearly divide the input space into class C1 and C2. If that is possible, then the data is called linearly separable. What is the example of a data which is not linearly separable? Let's draw a graph and understand when will it be not linearly separable. Let us say this is my input space and my red points which belong to class C1. Let us say those points are something like this. Okay. These are my red points. And let us say my blue points which belongs to class C2, they are something like this. These are my blue points and they belongs to class C2. In this case, there is no way I can draw a decision boundary, a line which will clearly divide this input space into two regions, in which first region has only red points and second region has only blue points. Let us say if I draw something like this, what will happen? On both sides, you can see there is a mix of red and blue. You can't clearly separate it into two regions in which one region only has red and the other region only has blue. That is not possible with a linear decision boundary here, right? So in that case, your data is not linearly separable. If it is not linearly separable, you can't apply linear classification there. That is the whole point. So you understood what sort of data you can apply linear classification on. Next thing is, how do you practically implement this? Let us say if you were doing linear regression, what would you do? You want to predict a target variable. Let us say some target variable t. What should this t be? It would be a real number, which is your value of y. Let us say you are predicting like y is equal to w transpose x plus w0. Let us say this is your equation. In this case, if it is linear regression, that is considering that you are solving a linear regression problem, what would you do? You would find this value of y. This value would be a real number. And what is this real number? This real number is your target. Let us call the target as t. This target is whatever you get as the value of y here. That real number is your target, and this is what you did in linear regression. Coming to classification, is it the same? Do you just want to find a real number? No, that is not the case. What do you want to do? You want to find whether this point x belongs to class C1 or class C2. This is what you want to do. There is no point in having a simple real number. So this time your target t should not be a real number. In case of classification, your target t should be just 0 or 1. 0 means class C1 and 1 means class C2. This is what you want. You don't want a real number. So if you want to, before that, this is in case it is two class classification. What if it is multi-class classification? Let us say you have 5 classes. Then how will your t look like? If you have 5 classes, then instead of t taking value 0 and 1, you will use something called as 1 of k encoding. 1 of k encoding, where k is your number of classes. So if it is 5 classes, then 1 of 5 encoding. How is that done? If it is in class C1, you will denote it as 1, 0, 0, 0, 0. This means it belongs to class C1, it does not belong to class C2, does not belong to class C3, does not belong to class C4, does not belong to class C5. In case it is class C3, how will you denote it? You will denote it as 0, 0, 1, 0, 0. This means it does not belong to class C1, does not belong to class C2, it belongs to class C3, does not belong to class C4, does not belong to class C5. So if it is a multi-class classification, this is the notation that you use in order to identify the class. That is, the target will look like this. If it is a two-class classification, you will simply use the target as values 0 and 1, where 0 denotes class C1 and 1 denotes class C2. Okay. So let us say you have this equation. What should this equation denote? This equation should give you a real number, but here you don't want any random real number. Instead, you want this real number to be in the range of 0 to 1. Why do you want it in the range 0 to 1? Because if this answer y is in the range 0 to 1, let us say 0.9 or 0.25, if it is a real number in the range 0 to 1, then you can interpret this as the posterior probability of the point belonging to one class, let's say point belonging to class C1. So if you know the probability that the class belonging to C1 is 0.9, let us say, then you can say this point belongs to class C1. And if it is 0.1, then you can say the probability of this being to class C1 is only 0.1, which means the point belongs to class C2. So when you were dealing with regression, you were okay with this y being any value, because whatever be the value of y, that is your target. But in case of classification, you are not okay with y taking any random real number. Instead, you want y to take a value in the range 0 to 1, so that you can take it as the posterior probability of the point belonging to one particular class. So in this case, you can't simply do W transpose X plus W0. Instead, you have to introduce something new, and that is the activation function. How does it work? This time it will be y is equal to function of W transpose X plus W0. And this function, this is called as the activation function. What does this activation function do? It will take the value of y to the range 0 to 1. So once you apply this activation function, the final value of y that you get, the real number, that will be a real number in the range of 0 to 1, which means you can interpret it as a probability. So this activation function, this function will be a non-linear function. You are using linear classification. It is a linear function of x, but the activation function that you're using, in order to bring it to the range of 0 to 1, this would be a non-linear function. And because of this, even though the decision surfaces are linear, that is what is denoted by W transpose X. Let's say this is your decision surface, this is your class C1, this is class C2. Even though your decision surface is a linear surface, because you're using a non-linear activation function, you call these sort of models as generalized linear models, which takes me to the next important point. That is, you would have thought that classification is way simpler than regression, because in classification, you simply want to say whether it belongs to class C1 or C2. Easy, right? And in case of regression, you want to find the exact value. That is, you want to find that the value is 22.1 or maybe 107.25. This is what you used to do in regression. But in classification, you simply want to say C1 or C2, which looks easy. And you would have seen that in many machine learning courses, you would see classification first. But here you are seeing classification last, because we already learned regression and then we are coming to classification. There is a reason behind. What is the reason? Because classification models are more complex. That is, if you can this is the reality. If you consider, let us say, linear regression and linear classification, in case of linear regression, you had a clearly linear model, that is W transpose X plus W0. When you found it, it was a very clearly a linear model that you used. But in case of classification, because of the presence of activation function, it is no longer linear in the parameters. This time it has a non-linear activation function, because of which what would happen? The model, it will have more complex analytical and computational properties if you compare it with a linear regression model. So because of this reason, classification models in general are more complex. So if you consider linear regression and linear classification, linear regression model would be a very clearly linear model, but the linear classification model, it will have a non-linear activation function, because of which it will be more complex to understand. This is the reason why we already learned regression, so you have the basic knowledge. We are going to learn classification, which will be easier for you and it will make more sense. So before we delve into the classification lectures in detail, we'll end this lecture with one more point. And we already discussed this point in some previous lecture where we discussed about three distinct approaches that you can use for classification. I'll have a very quick recap of that, because at this point you need to think of that again, because in the coming lectures we are going to go through these approaches for classification. We had discussed that there were three different approaches that you can use for classification. First one is to have a discriminant function. A discriminant function which would directly assign the input x to class 0 or class 1. This is the simplest way to classify, that you have an input x. What will you do? You'll take that x and put into the function. Then once the function is operated, you will get 0 or 1. So this function will directly assign x into class 0 or 1. This is called a discriminant function, and this is the simplest classification model. You would simply give x and the function will tell you whether it belongs to class 0 or class 1. This is the simplest model. What is the second thing that we discussed? Second thing is you find the conditional probability, that is posterior. P of ck given x. Given the data x, what is the probability that it belongs to class C1? You will find it P of C1 given, you will find P of C1 given x, and then you will find P of C2 given x. So if P of C1 given x is higher, that means it belongs to class C1. So here you have an inference stage. We discussed about inference and decision stages. In inference stage, what you will do? You will find the posterior, and in the decision stage, you will assign it into one particular class. Then we discussed about the third approach. What was the third approach? This was the generative approach, where we model the class conditional density. What is class conditional density? P of x given ck, right? This is what we did. We found class conditional densities, and then we used Bayes theorem in order to find the posterior. How do you find posterior from Bayes theorem? P of ck given x. How would you find this posterior? This can be found as P of x given ck into P of ck divided by P of x. What is P of ck here? This is the prior. So you will use prior along with the likelihood. Likelihood here is the class conditional density. Using the prior and the class conditional density, you can derive the posterior. This method is called generative approach. So in detail, we had discussed in the lecture where we discussed three different approaches to classification. So if you want to know in detail, you can refer that. Here I simply gave you a recap. That is, these three are the different approaches that you have for classification. So in the coming lectures, we'll look into this.